Okay, today we're going to talk about the layered architecture of ggplot, and then if time permits, what I will do, I will try to um, use, I'll try to introduce you to um, Google Colab, which you can use for both Python and R coding. So let me start my so can you see my can you see my desktop? Okay. So yesterday, last time when we discussed sort of a layered architecture and what it really means at the end. So I'll start from there. I'll quickly revise the concept of layered architecture, and then we will dive into the ggplot. So I'm going to use this empty class dataset as we did it last time. So here you have about 11 variables, and suppose we want to, our objective is to discover the relationship between miles per gallon and horsepower, the two variables here, miles per gallon and horsepower, and both of them are continuous. So we will do a simple scatter plot. So here is some basic scatter plot. So we did the summary, we got the minimum value, maximum value, we got the of minimum value and maximum value of the horsepower and miles per gallon. Then the first thing what we do in when we try to do introduce the layer concept of the plotting, first we create the landscape. Okay, so we create the landscape. This here we are doing the landscaping. So what is landscaping? Landscaping is basically, I'm saying that, okay, you just create a null plot, the limit of which will be 50 to 340, because, and I'm going to plot the horsepower in the in the x-axis. So minimum of horsepower is 52 and maximum is 335. So they will be within 50 and 340. And then y limit, the y-axis, I'm going to plot the miles per gallon. So y level, YLAB stands for Y level, that is MPG, and I'm going to restrict the limit of the y-axis between 10 and 35, because I found minimum of the miles per gallon is 10.4 and maximum is 33.9. So 35 is the upper bound. So first we run this piece of code, and that this gives me a just basic landscape. So this is, you can call it layer 0 or basic landscape or whatever. Then I'm going to draw a layer 1. I'm just going to do a grading. So once I put the grids, now we can remember the way we used to do when we were in school. We used to take this grid paper or the cross sheet, and this, now our cross sheet is ready. This is my layer 1 on the landscape. And now on this layer 1, I'm going to do plot the layer 2, where I'm saying that, okay, now you plot points on these things, you do a points. So now the points are ready and done. Then in the layer 3, I can say that, okay, draw some vertical line and horizontal line where the mean is 146.7 for the horsepower. So around 146.7, I will do a mean for the mean to represent the mean. So this dark red line represents the mean of the horsepower, and then I'll draw horizontal line. So this horizontal line represents the mean of the miles per gallon, 20.09. Okay. So this is the concept uh, of layered architecture. You can add another layer called layer 4, where I can just say that, okay, why don't you fit a straight line to these data points? So therefore, fit straight. So I can just say AB, and then I will just say miles per gallon, horsepower, color maybe blue, line width, LWD stands for line width. It fits the line. Notice that when you fit a straight line always passes through the mean of X and Y. And that is what you can see here. Typically, whenever you fit a straight line to X and Y, it always passes through the X bar and Y bar. And this is exactly what is happening here. So you can create these kind of plots on a layered architecture. This is the basic concept of the layered architecture. And this is exactly what we are going to do in the ggplot when we going to handle the ggplot. So the first thing what we are going to do is just first I'm going to do the call the ggplot, and then just run this line. If you do that, nothing will happen. But now, if you just run this plot thing, it just gives you the landscape. So if you just say ggplot data equal to empty cars, and the mapping equal to AES, aesthetic. AES stands for aesthetic. What is the aesthetic? The x-axis is horsepower and y-axis is miles per gallon. It just gives you the landscape. Now what you do, you remember that this entire landscape is there in the plot. Now I'm just saying in that plot, you add the points. So now you can see you have the points. Now I can put it into again in the plot. So I'll just put it in there. Now I'm saying that, okay, in this plot, you add a smooth linear regression. This is giving a message that this is using actually geom smooth using formula y tilde x. So it is fitting a straight line. In addition, it is giving a confidence band for the line. Okay. So these are the many additional features that are available for ggplot2, and that is kind of expected because these are like well efficiently written and all those things. Of course, you can change the points and all those things. So this is one way of handling the developing the ggplot. Now, so you can see that you can do it in a layer by layer basis. You can do the same thing. You can do the same thing by using the function called layer also. So what I will do, I'll just create this alternative. So let me just clean this. So again, I have the layer first, and then basic landscape, and then plot class, and write it as a layer, and then geometry, geom equal to point. If we just give this, okay, there is an error. I don't know. Generally it works, but I think maybe the new version has changed it. All right. So we can't use this. All right. I think it used to work, but now it's not working. But definitely this one it does work. So you can essentially, the way it works is you can just write ggplot. All you have to first basic layer data equal to empty. First, you have to give the data set name, and then even if you just write aesthetic AES equal to x equal to horsepower and y equal to mpg, then this is the first thing, and then you add another point geom first thing, and then you can add anything. You just add at the end of the function, you add a plus, and then just add that new layer. That's how it will work. See, that's how the whole idea of geom plot works.
Sir, LM is the linear regression one, right?
Say it again.
LM is the linear regression one, line that they are fitting. Linear regression line, right?
Linear regression. There is a package, in fact, there is a built-in function called LM fitting linear models. Okay. So it's in the stats package. This is available in the basic stats package. It's basically calling that LM. Okay. All right. Next, couple of things that you have done in the QQ plot. You can do it in this here also. Say so let me just copy this. So miles per horsepower divided by some other just maybe just trying to give this as say displacement. And if you run it like this, and then again, if you put this kind of things you can develop, and then you can add some, you know, okay. So if you don't give anything, it will fit a spline method. If you give anything, it will fit a spline method. So spline method oftentimes is very helpful in a sense, if there is some underlying behavior. So if I would have not fit the spline method, you probably would have fit in a straight line behavior. So this is oftentimes, so it looks like there is a very non-linear relationship between part horsepower, part displacement, and miles per gallon. So this kind of things you can discover using spline method. All right.
So what does that gray area represent?
It represents the confidence band. What does it mean? Have you heard about confidence interval?
No.
No. Okay. Have you heard about margin of error?
Yes.
What is margin of error?
It's the error in the prediction, like whatever that is predicted.
Correct. So basically, the concept of margin of error is if you are trying to estimate some parameter, right? How we estimate parameters? We estimate parameters by drawing random samples from the population, right? Now, when you are drawing a samples expected to be a random sample, then you are there will be some expected, error. That means why I'm saying error, that there is a true value here, but because it's a random sample, your estimate might be sometimes here, sometimes here. It depends on what sample you are getting around the true parameter, correct? So, so statistician and the probabilist and mathematician, they try to estimate that error. This error is called margin of error. Okay, or sometimes it's called, in statistics more precisely, it's called standard error. And then, which is basically about one standard deviation of the how much the error is on an average is deviating. Now, if you take two standard deviation,
Then is that from the z-score?
Z-score derived from there, but if you take a two standard deviation, then basically the error is somewhere between in that. I mean, you can say that actual value will be somewhere in that range. Okay. Now, here what they have done, that concept is being extended here, called confidence band. What does it mean? Now, see, let's take this value 0.8. At 0.8, if you try, say that if I tell you what is my horsepower, if my horsepower divided by displacement, this parameter is 0.8. At 0.8, what is my expected miles per gallon? So it will say that your expected miles per gallon is somewhere here, maybe 23, 24, right? But this is my estimate. What is the margin of error? 95% probability that it will be in this region. Your expected. I'm not saying that this will happen always. You may end up here, you may see here, but there is a high chance you will end up seeing the numbers miles per gallon in this region. That is called, now they have done that for everybody, every possible excess, and then they created a confidence band. So if you can think of any points, if you say 0.6, then your expected value is here in this position. Okay. And can you see my screen, my cursor that I'm moving?
Yes, sir.
So 95% probability that, so this is, I can make some error. The error is some, you may end up seeing it here or here or here, somewhere. But the 95% probability that your expected miles per gallon will be in this region. Okay?
So yeah, so confidence level is generally calculated like 2 times of standard deviation, like
Yes.
the standard or something like that.
I would say it's just a practice that
Okay.
developed by over the like academic world and the industry world
Yeah.
over years of practice. Yeah. All right. Any other question? Okay. Next, I'm going to do one more thing. Say, I can do one more thing here. So in the aesthetic part, you can add also color. Color equal to okay. To add this, apparently it will not do anything, but now you can see there is something different. So basically CYL stands for cylinder, how many cylinders the engine has, and then so interestingly there is some kind of a behavior we are kind of seeing. So now what is happening? Can anybody tell me?
Fitting different curve for different colors.
Tell me. I can't follow you. Can you please?
Like fitting different curve for the different
Very
like
good. Yes.
clusters or something.
Yes. And okay, yes, that is what is happening. But what is your analysis? What is your analysis from? I mean, see, fitting curve is not a big deal, but what is your analysis from this? Anybody can fit car. I mean, just that is not a big deal. Think about it. Okay.
Sir, what is this CYL? Can you say once again?
Okay, Ujjwal is saying no outlier. Fine. What else?
Like sir, for a given, like the higher number of cylinders for a given horsepower upon displacement, we'll have higher MPG.
Right. So what does it mean basically? Okay. First of all, you see all the curves are almost flat, correct? All the curves are almost flat. So that means essentially it's saying that horsepower by displacement does not have any effect of miles per gallon if you do try to fit it using by color. If that is number one. Number two is, say, take the red ones. Red ones is the four-cylinder cars. Overall data has 32 points, and how many points we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Only 11 cars, or 11 points are four-cylinder cars. When we are using only 11 points to fit a very nonlinear regression curve, what is happening? My confidence band is increasing. Like previously it was like this, now confidence band is like really big. What does that mean? That means my margin of error is too big, standard error is too big. Effectively, we can't make any statistical valid inference using this graph. And that is the key learning from this graph. It might look very beautiful, oh, it looks very fancy, but what it means, does this analysis make any sense? So that is the very important part of any statistical analysis. So technically, how many variables we are trying to model here? You look at miles per gallon, horsepower, displacement, and number of cylinders. So 4 variables I am trying to plot it in this graph. And on the top of that, we are trying to fit smooth curve using the by groups. And as a result, what is happening? It's basically fitting it did not able to do any justice. Okay. Clear? Okay, there's something. All right. Um, so I'm leaving the analysis part for you guys. You just fill it up, whatever you're learning with this. And then couple of small things that I want to do. Just a minute. So I would. So if you ask me that if I want to put, so I would not put too many variables like in one single graph, or this always makes the whole thing very cumbersome. But I would definitely try to put some, if it makes sense, it does make sense, then I'll try to put some, I'll try to play around with was missing. Play around with the color, so you can, that I will definitely try out. So on dark blue or red, so those things I will definitely try out. So these are that you can do within the geometry, the geom point. You can just put the different color, and that it will keep changing. It will give you the color that you would like, what you are liking. All right. Um, One thing probably you may try, but I don't know whether it will work or not. So instead of geom smooth, you may try geom line, but I think it will just create a flat line. Yeah, it's just joining the points. So this is a geom line is particularly good for time series kind of data. So it doesn't fit a line. So if you want to fit a case by case line, probably you have to give a smooth, and then I think method equal to, you have to specifically mention, yeah, that fit a straight line kind of thing. And that does at least, what happens is straight line, fitting a straight line is much more, what is the right way of saying it? Some much more simpler than fitting a spline method. Spline method is much more complex. It has too many parameters, and as a result, the margin of error increases significantly. So that is what you are seeing here. Okay. Couple of other things I will try. So suppose I want to do a cylinder like this, and then I want to create, okay, let me just first do that and you will know what I'm trying to do. I think it will, so this is not the right one, just a minute. Slot. It's not working. So actually what I'm trying to do is I'm trying to create a side-by-side box plot. So one way of doing it is simply you just say X per gallon as a function, cylinder, and then data equal to MP cars. We'll just do a side-by-side box plot. And so this is very helpful understanding how different by group, if you have a categorical variable, like here cylinder, 4-cylinder, 6-cylinder, right, 8-cylinder, different kind of cylinder. It's sort of a 3 category variables. Then they have a, of course, there is a ordered behavior, and as the number of cylinder increases, the entire distribution is sort of a, there is a non negative relationship between cylinder and the miles per gallon. But since it's a categorical variable, technically we cannot apply sort of a scatter plot kind of behavior. So one thing we can always do is we can just plot it as a box plot, because miles per gallon you can think of as a continuous variable, but number of cylinder if somebody has some car has a 4-cylinder car, it is 4-cylinder. So side by side box plot is very helpful in that way. And so if you put PCH, you can see there is a outlier. That can make it slightly bold. You can choose color. You can make it, I think, horizontal equal to 2. If you just, you can make it sort of a horizontal, and then you can give color as, let me just, orange, white, and green. I'll just choose it. So this kind of small stuff you can do. I'll check it out how you can do a small ggplot, box side by side box plot in this case using ggplot. I'll check it out and I'll show you guys. All right. Next topic that I would like to discuss today is called you can use Colab, which is basically a Google product that you can use. There are a lot of, I think, just a minute. So I'll just go to my Google Drive. So Python programming, you guys are using Jupyter Notebook, right? This is essentially Jupyter Notebook on Google Cloud, you can think of. So there are a lot of advantages that you guys can take off. So if you go to the new thing and then go to more, you can see Google Collaboratory. This is in short called Google Colab. Okay. By default, Google Colab works as a Jupyter Notebook. Okay. So let me show you a few stuff. So I have a, so you can just literally, this is the code 2 + 2, and if you just run it, so in first one it will take cut, connect, and then in the text, whatever.
So we have Colab in our Python class. We know the basics.
Okay, are you guys using it, Colab, in all of you?
Yes, sir. In Python course, Madhavan sir is using this to teach in course itself.
He is using Colab or local Jupyter Notebook?
No, he's using Colab.
Oh, wonderful. So you guys are already familiar with Colab. That's pretty cool. You can use Colab for your, for R coding also. So only thing that you have to do is this small piece of code you have to run, and to be in the beginning. And then whenever you're writing a R code, in that R code, you just R code should start with this percentage R, and that will load the basically for that code chunk. You can run it. So yeah, you can. So let me just run some code. Maybe I'll just take this piece of code. Here, just run this piece of code. You can see the R code. You can run the R code also in the Google Colab. So this is very useful, particularly when, as you guys know, at the same time, you can run the Python code also. So in the same notebook, you can run your R code as well as your Python code. So this is very helpful, I found. So this is one of the thing I thought I would like to you guys to see. All right. So I'll just go back. Say that's close to miles per gallon. Then if you just say histogram, it will show. Okay. So it will do like this. So you can just say main width. So you can try, by default, it takes the 0.1. So that's why it was creating for each point, it was creating something like this. So you can draw the histogram like this, and on the y-axis, if you want, say density, so you have to write it like this. I think it will work. Yeah, so it can give you the density. And 5 is just fine because we don't have much data. All right. I think I will introduce, so now you know histogram. I would like to introduce, so some of the, one of my idea is to introduce you guys to some of the statistical concept using visualization technique. And I found those are very useful oftentimes when you are talking to non-statistics, non-data science community. So let me start a new script. Is Shiva started the concept of sampling distribution?
Yes, sir.
Okay. What he has done so far? So what is sampling distribution?
We are taking sample from some known or unknown distribution, and then we are trying to figure it out that uh, what that distribution will look like in general. So,
Okay. So what has he done so far?
sir, I don't think
Hmm?
class.
I don't
Hmm?
think so, what you're asking for is yet completed in the course.
Uh,
We
sir,
have just
basically, he has not given the complete idea of sampling distribution, as in um, the small samples or like that, but CLT he discussed.
Okay.
So the basic idea of sampling distribution from CLT he has discussed.
Okay. Okay, fine. So we will use visualization to understand what is sampling distribution. Okay. Hmm. All right. So what I'm going to do, and the idea is, suppose, let us take a slightly bigger. Acha, let's take the let me just give an example. So you have this concept. Suppose we have a random sample. So let's take this data set. Okay. And you have this samples. These are the real samples, right? There are 32 values of miles per gallon. Now, if I ask, so typically what are the parameters we are interested in? We are interested in mean. Okay. We are interested in variance. We are interested in standard deviation. Correct. But the question is, so these are estimates. This is estimates, right? So suppose there are 32 cars that have been randomly sampled from the world car populations of some billions of cars. The 32 cars were randomly sampled, and their miles per gallon were measured and given to you. And based on that, you just calculated 20.09, and you are saying that so I can assume that, okay, maybe miles per gallon do follow some kind of normal distribution with mu or and sigma square. Okay. It might be possible that miles per gallon, actually miles per gallon will more appropriate will be maybe a gamma distribution, because miles per gallon will never be a negative value, probably a gamma distribution with some parameter a and b. So it has its mean. Definitely this gamma distribution has some mean, and that mean, I'm just saying that, okay, this mean is being approximated with 20.09. Now the question is, now I'm going to do a thought experiment. Okay. The thought experiment is this. So say in the class, I'm asking, so 50 of you are here in the class and asking everybody that you go and pick all the four-wheeler personal cars that are available in the area. 32 such cars you randomly pick and write down their miles per gallon. Okay, so what will be your data set will look like? So it will be like this, like first student one, and student one has take the value of car one to student car one, car two, in this way 32 cars. The first student goes, say call one, I'm just giving an ID, and suppose this is 34, the second one is 26, then 20, then student 2 who has gone, and the first card they she or he chooses 14, 22, 3, number, say 27. In this way, you can now got in this way. Say I have asked 50 students in the class, all 50 students goes and collect the values. And we don't, in that case, we don't rely on the empty cars data set that we have in our R base R. Okay. And one thing we do ensure that all of you have drawn the card in your area randomly. That we did ensure. Okay. So that part we did ensure. And all of, so now once you calculate, then what you can do, you can calculate the mean. So all the, what we can do, we can calculate take these values and calculate their mean. So mean is here 21.8. Then we can say that, okay, this is 29 point, so 19 point. Second students who in this way 23. Similarly, we can compute the standard deviation, compute the skewness, all the kind of stuff we can compute. Okay. Now we have 50 such means. Now what we can do, we can compute we can look into think of drawing a histogram of these 50 such means. Okay. And that 50 such means will give me a distribution like this. That distribution is called sampling distribution. Clear?
be normal distribution, right? Because as CLT.
Huh?
It will be
Many such. I have not reached CLT yet. CLT is far from here. I'm just discussing the sampling distribution, concept of sampling distribution.
Can you please repeat the last sentence you said?
Okay, very good. Is the experiment clear? The thought experiment clear? So I'm
Yes, it
asking
is clear.
clear.
It is clear.
Now for each student, you can compute this mean. So you have 50 such sample means.
Okay.
You can think these 50 sample means as your data and you can draw a histogram.
Yes, I can.
That histogram gives you a nice distribution. And that distribution is called sampling distribution of sample mean.
It is clear now. Thank you. It is clear.
Very good. Similarly, you can do it for standard deviation. You can, for each student, you can calculate the standard deviation. So I have now 50 such standard deviation. All these standard deviations, you can calculate and you can draw a histogram of the standard deviation, and that standard deviation, that distribution can be called sampling distribution of standard deviation. And why it is called sampling distribution? Essentially, it's a probability distribution, but this is coming from a sample. This is about this probability distribution is the probabilistic property of a sample. So that's why it's called sampling distribution of sample mean, sampling distribution of sample standard deviation, sampling distribution of skewness, correlation. Any parameter you can think of, you can come up with the sampling distribution through this thought experiment. This thought experiment is extremely important to understand the concept of sampling distribution. Clear? Now what we can do, we can create a simulation study. How we will do the simulation study? So let us simulate from, from the gamma distribution. Okay, let me just, there is something called R gamma, which will help us to simulate from the gamma distribution. So there is a rate and scale. I always get little confused with shape, rate, and scale. So I think shape is A, scale is S. So scale is S, and expected value of, if my X is following gamma, then expected value is A times S, that is set shape times scale, and variance is of X is A times S square. Now what I'm doing, let me just write the simulation experiment. So let's take, and assuming that X is miles per gallon, which is following gamma, some parameter A and B is where maybe expected value of X is say 20, and variance of x is, what's the variance? Say 36, so 20 and 36. Okay. Variance is 36. Now I have to solve for a and s. So s times s is 36. So s will be 36 by 20, which is 1.8. And a will be then, so a times s is 20. Let me just take 20 here. Okay. It's 20. Then a is 20 divided by 1.8, 11.11. 11.1 approximately. So let us assume this miles per gallon is following a population distribution, say gamma equal to 11.11 and s equal to 1.8, where shape equal to a and scale equal to s. So first let us simulate from miles per gallon from the gamma distribution. Let us plot and see how it looks like. Okay. So what I will do, I'll just simulate x from r. Let me just first set.sid. Set.sid always else. Okay. So gamma in equal to say 1000 and should equal to 11.11 and scale equal to 1.8. So let me just run this. It's there. Let me do a histogram. So So that's how it looks like. Okay. So this is the popular, that's, and actually if I really plot let me just do a sort. Comma d gamma. So this is the true density is equal to shape equal to 11.11 and scale equal to 1.8. Yeah. So that's how it's. Let me just do. Great. So it will look a little better. So this is the true density. This is the true population density. I'm assuming it is gamma with, you know, somewhere in the range of 10 and 50. So it's somewhat thick. Okay. So it's original population density. Fine. Now, what we are doing, we are going to draw a random sample of size 32 from gamma distribution, and for 50 times for 50 students, and we will draw a histogram. Okay, so what I will do is the first thing I will do is, let me draw a random sample of size set. First, I'll do 32. Okay, and then so this is the random sample, and then scene size is for 50 students. I'm just trying to keep the whole thing with the thought experiment. 50 students. Scene size, that is the simulation size. Because remember that in my thought experiment, in reality, we have only one data. This, in reality, we will have only one sample. We will never have a 50 samples. We will have only one sample. We will not have a infinite resources. Thought experiment, we have infinite resources. We can do 50 samples. And can tell me why 50, sir? If I have infinite resources, I can go 50,000 samples. Of course, we can do 50,000 samples. But for the time being, let's keep it simple. 50, we will increase in my simulation study. But in reality, we have only one sample. Okay. So what I'm going to do is, I'm first going to sample, say, MPG star from R gamma equal to, say, here n. So this n is here n. R gamma itself has a n, which is a sample size, and then shape and scale, and this. So if I draw a random sample, sorry, right? This is the randomly sampled values from a gamma distribution with shape equal to this parameter and scale equal to this parameter. Shape equal to 11.11, scale equal to 1.8. And then what we can do, we can just compute this value 20.31. Okay. Now, what I can do, I can just create a loop. I want to simulation size the 50. In bracket, I will just keep it like this, and then what I'll do, I'll just click sample. I'm just creating a vector place with some size. So basically, if I run this, so I have a vector of 50, size 50, and that thing is empty. Okay. And then I'm saying just on the ith place, you go and keep this sample size. Sample B. So need to put the set of sit here, because before we run the thing, because every iteration, it will draw a random sample from the gamma distribution. Since it is drawing a random sample from gamma distribution, I'm setting the seed right before the loop, because if you do that, then the final result that I'm getting and you are getting will be same. But if you don't want to do that, perfectly fine. So let me just run this. So now these are the 50 samples that you got. Okay. If you got 50 samples, perfectly fine. And then what I'm going to do is I'm going to draw a histogram of this sample mean. So this is what you are looking like. So that is how, so I can say this is the sampling distribution of sample mean. Does it look like a normal? What do you think?
Yes, sir, it will.
Somewhat on the right hand side, it does look like normal.
Okay. How many of you think it doesn't look like a normal?
Sampling size is too small, so it won't look like.
It is not a normal actually. I'll tell you why. And I'll argue for that it is not normal. Why? Look, population distribution is not a normal. So the sample size is only 32. So it will not behave like a normal. It will be something else. It will definitely some distribution, but it is not normal. So let us run it for a few more times. So we have only 50 simulation size. Let us increase the simulation size to 500. Probably we will get a slightly better sense of how this sampling distribution looks like. So now it is probably behave little better. What about 5,000? Okay. What about 50,000? So it looks like normal when we are increasing the simulation size.
Sir, but anyway, even if I have like a 50 size simulation size, then it's a part of a normal distribution, right? If we are increasing the simulation size, then it is showing that normal, in a
It is
better way.
not, just a minute, just a minute. I am not finished my thing. Okay. Just hold your thought. I have not, just hold your thought.
Okay, okay.
There are a lot of issues are here. Don't jump into conclusion. Maybe you know some of the things from your undergrads, but just hold your thought. I'll show you these simulation studies, very important. Now what I'm going to do, instead of 32, I am going to take only 5. So that means each student is drawing only 5 samples, but my simulation size is 50,000. And let us see how it behaves. Still, it behaves like a normal thing, but pretty well actually. But technically, we can show there is something called ggplot, which tells us whether it's normal or not. But sample mean is typically it will not be like exactly normal. Okay. Q norm actually. So it will be against. So if you look into the QQ plot, it will be sort of almost like a normal, but on the tail part, you will see that. So what happens in the QQ plot is it's compared against a sample which is drawn from the exact normal distribution. So if your generated sample is from the normal, then all points will be fall in this line. But you can see that this tail part is actually away from the normals. Okay. So that means that this distribution this sampling distribution may be a bell-shaped, but bell-shaped behavior does not mean that it is normal. There is a lot of other distribution which can behave like a non-bell-shaped. For example, for certain choices of gamma distribution, it can behave like a bell-shaped. There is a distribution called T distribution, which behaves like a normal bell-shaped. Logistic distribution behave like a bell-shaped. Cauchy distribution behave like a bell-shaped. So there are a lot of other distribution which behaves like a bell-shaped. So if you just look at the histogram, which is bell-shaped, that not necessarily that means it's a normal distribution. And ggplot is ensuring us, telling us that yes, it is not normal distribution. How the ggplot behaves. So on the x-axis, what it does, on the x-axis, it simulates from a normal distribution. Okay, and then plot the quantiles. So on the x-axis, if the data would have come from the normal distribution, then these would have been the quantiles of the normal distributions. And then on the y-axis, it plots the sample quantiles from the data. Now, if the data was actually coming from a normal distribution, then the sample quantiles and the theoretical quantiles would have on the exact 45-degree line. But what we are seeing, these on the tail part, definitely on the tail part, on the body part, with the bell-shaped part, it's on the line, but on the tail part, it is behaving very differently from normal. So though the distribution, sampling distribution behaving almost like a normal, but the tail part does not behave like a normal distribution. Clear? This point is with you guys. Now what I'm going to do, I'm going to increase the sample size. So that means these 50,000 simulation or 50,000, if in your thought experiment, if you assume there are 50,000 students who are going to the field, collecting the data, each of them were collecting only 5 samples. Based on that, we computed the sampling distribution of sample mean. And we found that sampling distribution of sample mean behaves like a bell-shaped, but the tail part does not behave like a normal distribution. Now we are going to increase the sample size. Sample size, now we are going to increase it to 30.
You're not sharing your screen right now.
Oh, sorry about that. Can you see it now?
Yes.
Sorry about that. All right. So now I'm going to increase it from 5 to say 30. What I'm going to do is from the same code. Now it still behaves like a normal. Now if I plot the ggplot, now you see this is almost on all the points are almost on the straight line. So previously when I had the sample size 5, sample of size 5, that's how the ggplot was. So you can see that body was behaved like on the normal, but the tail part was very different than normal distribution. So the distribution on a visually looks like bell shaped, but just because it is bell shaped, you should not conclude that it is normal distribution. It could be far from the normal. In fact, we are seeing when we have a sample of size 5, the actual sampling distribution of sample mean is though bell shaped, but tail behaves very differently. When we increase the sample size from 5 to 30, it is now behaving very close to normal, but not normal, yet not normal, because we can see that it is much better than sample of size 5. Now, if I increase it to say 50, almost all points are on the normal, except few points little bit ahead. Let us take a sample of size 80. So now almost all points are on the normal. So as the sample size is increasing, my sampling distribution initially was not like a normal, but now it is behaved like a normal distribution. My sampling distribution of sample mean is behaving like a normal distribution, and that is what central limit theorem tells you. Any doubt? Few more things I would like to do. Slim. Okay. So from 10 to 35. All right. So let me just run this. So when we have sample of size 5, so what I am going to do in the histogram, I'm saying that you keep your X lim fixed from 10 to 35, and we will see there is a remarkable change in the pattern and the behavior. So let us run it. So this is the sampling distribution of sample mean, and this is the ggplot. Now I'm going to increase it to 30. So this was sample of size 5. So let me just, for the time being, let me just clear it up. And when I have 5, sample of size 5. So this is my sample of size 5. When that's how my histogram looks like. When I'm increasing the sample size from 5 to 30, you can see how the samples distribution looks like a bell shape better than, and it actually got shrink. Now, if I increase it to 80, it's getting even. So if I use a sample of size 5, then sample mean, I'm saying any random sample you choose, and their mean will vary in range of say 15 to 25. 95%, that is where the 95% confidence interval comes in. As I increase the sample size from 5 to 30, Now my sampling distribution behaves like very sharp. As it is it's very sharp, the chance that my 95% of time, whatever random sample you pick, because you have a lot of sample now, instead of 5 to 30, it's like 6 times bigger sample. So most likely your sample mean will be somewhere in the range of 18 to 22. Then when you are increasing your sample size from 50 to 80, it may be between 19 and 21. So it's even sharper. So your confidence interval is coming. So basically your standard error is dropping, your margin of error is dropping, your confidence interval will get like 95% of time or 99% of time, you will get you get to see your sampling distribution between this confidence interval. Okay. Anybody have any doubts? Now you can do the same thing. We have done it for the mean, but nobody is going to stop you to do the same study for variance, sample variance. Nobody is going to, doubt you for sample standard deviation or some correlation coefficients. So I'm going to assign assignment.
I didn't get that. Could you try again?
I'm going to assign I'll assign an assignment where basically you have to do this simulation study and draw the histograms using ggplot. And for sample mean, sample variance, and you will see that these things. So last thing before I stop, so you can do the same thing. Instead of here, you can do so instead of sample mean, you can just take the sample variance. And then sample variance is, you can just take sample variance equal to I equal to variance of star, and you run it. This maybe I'll just 30. And you can run histogram of sample variance. Oh, I don't know. Sample variance will probably take maybe 5, maybe 90. Yeah. So sample variance, this is the sample variance. So variance can vary from very large range. So, and we can see that sample variance is a very positively skewed behavior. So, and which is probably makes sense because we do know that sample variance have a chi-square distribution, scaled chi-square distributions. Now, okay. Next is, I think I'll stop here now. It's almost 12 o'clock. So I'll stop here today and I'll assign this assignment. Also, I'll send you an email regarding the